Welcome back. We're now starting week 7. This is the first lecture in week 7. We're going to continue on with our mechanical considerations. This week we're going to look at taking different processes and checking for some sort of form of waste heat coming off these processes. Specifically, we're going to look at trying to recover some energy from waste hot water. It's surprising how many different processes out there have a lot of waste hot water. Laundries, textile dye baths, various types of process cooling systems, food processing, and other wash operations have a significant amount of water that's got a lot of heat in it. This waste hot water, at least at minimum, can be used to preheat the supply water for the original process that we're looking at. Now, a key aspect of this is actually the condition of the water. The water must be usable in a heat exchanger. So looking at that, the wastewater must be relatively clear so that fouling of the heat exchanger is minimal. Otherwise, you end up with so much service, it doesn't really pay for itself, whatever energy you're saving extracting out of the water. The water also must be minimally corrosive, also to minimize the damage to the heat exchanger. Now, there's two types of heat exchangers, as you recall from your heat exchanger section in your 462 or 362 class, shell and tube and plate and frame. Shell and tube is a little more tolerant of more junky water. Unfortunately, it's one size when you start. Plate and frame has a lot more variability to it. It's a little more expensive on first cost, but you can change the plates out to vary with the situation you're in. You can change depending on the load over time, and you're able to get a lot tighter delta T on the extraction side. So it's really up to you and your heat plate or heat exchanger manufacturer decide on what's the best. The heat exchanger choice will be dependent on the wastewater. Now, when you go to the heat exchanger manufacturer's specification sheets and start doing analysis, you're going to get a resulting temperature rise that can be applied to this particular situation and a particular heat exchanger. This temperature rise off the heat exchanger is needed to calculate a potential cost savings. Now, there's a combination of field-derived measurements and spec data from the heat exchanger manufacturer within this formula. So if you look at the base formula, it's really the heat transfer for a fluid, specifically water. So it's BTUs per hour, which would be the 500 times the delta T times your flow rate, the GPM. And the rest of it should look familiar. You're going to have a fuel cost. You're going to have the number of hours per year that the process is in operation, divided by the heating efficiency for that hot water in the process to start with, and how many BTUs are in the particular fuel that is being purchased. Now, the process uses, in this particular example, 28 gallons per minute. This is a field measurement. The temperature rise, which we determined at 25 degrees, came working from a heat exchanger manufacturer looking at various types of heat exchangers and specifications on the heat exchanger. This turned out to be the optimal between first cost, area where we can put it, installation cost, operation, variations in the operation. So a number of factors went into that. The process itself operates 2,100 hours a year. The heating efficiency on that overall process is 83%. Natural gas is currently being purchased at 88 cents per 100 cubic feet, and 1 CCF is equal to 100,000 BTUs. So if we put those values into the formula, We have the 500, which is a given for water, times the temperature rise, times the flow rate of the water in the process, times our energy cost, times the hours per year that the process runs, divided by the efficiency, divided by the fuel BTU content, and we get $7,792.77 per year. And again, it's important to notice that, again, a lot of these hand calculations use formulas that you're already familiar with. Another heat transfer formula. This one happens to be for a fluid flow or water. This will work with other fluids. You just can't use 500. You have to use whatever that constant is for that particular fluid. The other thing, when doing energy audits, you should always be on the lookout for waste heat not being used. This ends Lecture 7A. When you're ready, you can proceed to Lecture 7B. Thank you.